Hi everyone, and welcome to Praxis IB. In this lesson, we are going to learn how computers actually store and work with information. That's topic A1.2, data representation and computer logic. Now, I want you to relax because we are starting completely from zero. You don't need to know anything before this video. Here is the big idea to hold on to. A computer is, at its heart, an incredibly simple machine. It can only understand two things, electricity flowing or electricity not flowing. We write those two states as the number 1 and the number 0. That's it. Everything else, the photos on your phone, your favorite song, this very video, is somehow built on of just ones and zeros. Sounds impossible, right? By the end of this lesson, you will understand exactly how it's done. We will learn the number system computers use, how text, images, sound, and video gets turned into ones and zeros, and then how computers make decisions using something called logic gates. This is examined on paper 1 for both standard level and higher level, so it really matters. Take your time, pause whenever you need to, and let's begin. Before we dive in, let me show you the map of where we are going, so nothing feels like surprise. The syllabus breaks this topic into 5 parts and we will follow them in order. Part 1, the different ways of writing numbers. You have used one of them your whole life without knowing it has a name. Part 2, how a computer takes real things, like a sentence or a photograph, and stores them as ones and zeros. Part 3, logic gates, which are the tiny decision makers inside every computer. Part 4, truth tables, which are just neat ways of writing down what a logic gate does. And Part 5, logic diagrams, where we draw circuits using simple symbols. Notice how each part leans on the one before it. You can't understand logic gates until you are comfortable with binary. So we build up slowly, brick by brick. One quick note for the exam, examiners often mix these parts together in a single question. So don't think of them as 5 separate topics. Think of them as 5 chapters of one story. Alright, let's start with chapter 1. Let's begin with something you already know better than you think. When you count 1, 2, 3 all the way to 9 and 10, you are using a system called denary, also called decimal or base 10. Why 10? Almost certainly because humans have 10 fingers. In denary, we have 10 different symbols to work with, 0 through 9. Now a computer doesn't have fingers. A computer only has those two states we talk about, on or off. So a computer counts in binary, which is base 2. In binary, you only get two symbols, 0 and 1. That's the entire alphabet a computer works with. Finally, there's a third system called hexadecimal, or hex, which is base 16. Hex uses 16 symbols, the digits 0 through 9, and then the letters A, B, C, D, E, and F to represent the values 10 through 15. Here's the part students always get confused about, so listen carefully. The computer doesn't use the hex inside itself. Hex is purely for us humans. Binary numbers get really long and really hard to read, and hex is a short, tidy way for people to write them down. Think of those color codes you might have seen, like hashtags FF0000 for that. That's hexadecimal, for example. So, denary for humans counting, binary for the computer, and hex as a human shortcut for binary. Keep those 3 roles clear in your head. Okay, let's actually learn to read binary, and I promise it's easier than it looks. First, let's remember how our normally denary numbers work. Take the number 342. The 2 is just 2, but the 4 isn't 4. It is 4 tenths because of its position. And the 3 is 3 hundredths. Each position is worth 10 times the one to its right. That idea that digit's position gives it a value is called place value. Binary works in exactly the same way, except each position is worth 2 times the one to its right instead of 10. So starting from the right, the positions are worth 1, then 2, then 4, then 8, 16, 32, 64, 128. Those are just the powers of 2, doubling each time. Now here's the magic. To turn a binary number into a decimal number, you look at each position. If there's 1 there, you kept that position's value. If there's a 0, you ignore it. Then you add up everything you kept. Let's try the number on the screen. 1 0 1 1 0 1 1 0. Going through the positions with a 1 in them, we keep 128, then 32, then 16, then 4, then 2. Add those together. 128 plus 32 is 160, plus 16 is 176, plus 4 is 180, plus 2 is 182. So that binary number equals 182 in decimal. Reading binary is really just adding up the columns that are switched on. By the way, 8 of these positions, called 8 bits, can hold any value from 0 up to 255. That's why the number 255 pops up everywhere in computing. Now let's go the other way. We have a normal number and we want to turn it into a binary. The method is called repeated division by 2, and it's very mechanical once you have seen it. Here is the rule. Divide your number by 2, write down the answer, and importantly, write down the remainder. That's whatever is left over, which will be always either a 0 or a 1. Then take that answer and divide it by 2 again, writing down the new remainder. Keep going until you have divided all the way down to 0. Let's do the example of the number 156. 156 divided by 2 is 78. Remainder is 0. 78 divided by 2 is 39. Remainder is 0. 39 divided by 2 is 19. Remainder is 1. 19 divided by 2 is 9. Remainder is 1. 9 divided by 2 is 4. Remainder is 1. 4 divided by 2 is 2. Remainder is 0. 2 divided by 2 is 1. Remainder is 0. And 1 divided by 2 is 0. Remainder 1. Now here's the crucial step that everybody gets wrong the first time. You read the remainders from the bottom to the top. Reading bottom up gives us 1 0 0 1 1 0 0, which is 156 in binary. If you read them top down by mistakes, you get the number backwards, so be careful. One last tip for the exam. Questions usually want an 8-bit answer. So if your binary number is too short, pad it with zeros on the left until it's 8 digits long. And always show all your division steps. You earn marks for the method itself, even if you make a small slip at the end. Let's bring back hexadecimal and see why it is so handy. Remember, hex is base 16 and binary is base 2. There's one beautiful fact that links them. Exactly 4 binary digits make up exactly 1 hex digit. 4 bits, by the way, have a name. They are called a nibble. Because of this, converting between binary and hex is almost no work at all. You don't do any arithmetic, just chop the binary number into groups of 4, starting from the right, and translate each group on its own. Let's look at the example. We have the binary number split into 4 nibbles. The first group, 1 1 0 0, equals 12, and 12 in hex is written as the letter C. The next group, 0 1 0 0, is 4, so that's just 4. The next 0 1 1 is 7. And the last 1 0 1 1 is 11, which is hex is the letter B. Put them together and that whole long binary number becomes simply C47B. Look how much shorter that is. That's the entire point of hex. It takes a square string of 16 ones and zeros and turns it into 4 each character that a human can actually read and remember. This is why programmers write memory locations and color codes in hex. A tip: if you ever forget which hex digits matches a nibble, just quickly work out the 4-bit value using your place value columns. 8 4 2 1, and always group for the right hand side. Let's talk about how we measure amounts of data, because you have definitely seen these words on your phone or laptop. The smallest unit is a bit. That's a single 1 or 0, the tiniest piece of information possible. 4 bits together make a nibble. which we just met, 8 bits make a byte. And a byte is really important unit because 1 byte is enough to store a single character, like a letter A. After the byte, the units get bigger. A kilobyte, then a megabyte, then a gigabyte, then a terabyte, and then petabyte, each one much larger than the last. Now here's a trap that catches almost every student, so pay attention. In everyday life, kilo means 1000. But in computing, 1 kilobyte is not 1000 bytes. It is 1024 bytes. Why such a strange number? Because computers work in powers of 2, and 2 to the power of 10 happens to be 1024. Every step up the ladder multiplies by 1024, not 1000. Here's a real example you may have noticed. You buy a hard drive that says 500 gigabytes, but your computer reports only about 465. The drive isn't broken. The manufacturer counted the thousands while your computer counts in those proper binary units. For the exam, when you do a calculation and end up with bits, divide by 8 to get the bytes. Then divide by 1024 to climb each step. And always keep track of which unit you are in. So far we have only stored positive whole numbers. With 8 bits and ordinary binary, you can store any number from 0 up to 255. We call that unassigned, meaning there is no sign, no negatives. Every bit is used to make the number bigger. The largest value you can hold is 2 to the power of n, minus 1, where n is the number of bits. Now, this next part is for higher level students. If you are taking standard level, you can relax through this bit. The question is, how does a computer store a negative number, like minus 5, when all it has is ones and zeros? The answer is a clever trick called 2's complement. The idea is that the leftmost bit, the one worth the most, gets a special job. It becomes the sign bit. If it is a 0, the number is positive. If it is a 1, the number is negative. To actually create a negative number, you follow 2 steps. First, write out the positive version in binary. Second, flip every single bit. Every 0 becomes a 1 and every 1 becomes a 0. And then add 1 to the result. Let's do minus 5. Positive 5, 8 bits is 0, 0, 0, 0, 0, 1, 0, 1. Flip all the bits and you get 1, 1, 1, 1, 0, 1, 0. Now add 1 and you get 1, 1, 1, 1, 1, 0, 1, 1. That's how computer stores minus 5. Using this system with 8 bits, you can represent numbers from minus 128 all the way up to plus 127. A higher level exam tip. The mark scheme literally looks for the phrases invert all the bits and add 1. So say those exact words and show every step. Now let's see how a computer stores words and letters, because obviously a computer can't store the letter A directly. It can only store numbers. So the solution is simple. We agree on a code, a giant lookup table, where every character is a given number. Then we just store that number in binary. The oldest and most famous of these codes is called ASCII. ASCII uses 7 bits per character, which gives it room for 128 different characters. That's enough for the English alphabet in capitals and lowercase, the digits, and common punctuation. Let me show you with a real example. In ASCII, the capital letter A is assigned to number 65. And 65 in binary, written in 8 bits, is 0, 1, 0, 0, 0, 0, 0, 1. So when you type a capital A, that's the pattern of ones and zeros the computer actually stores. But here's the problem. 128 characters is nowhere near enough for all the world's languages. Think of Chinese, Arabic, or even emojis. So a much bigger code called Unicode was created to give every character in every language its own number. And UTF-8 is the most popular way of storing Unicode efficiently. It's clever because it's fully compatible with the old ASCII code, and it's what most of the internet uses today. For the exam, you don't need to memorize the codes themselves. You just need to remember the chain. A character becomes a number, and that number becomes binary. And remember that capital and lowercase letters get different numbers. Let's tackle images. Zoom right into any digital photo and you will find it's made of thousands of tiny squares called pixels, arranged in a grid. Each pixel is just one solid color. So if we can store the color of one pixel, we can store the whole picture. How do we store a color as a number? We use the RGB model. RGB stands for red, green, and blue because you can make almost any color by mixing those three together in different amounts. For each pixel, we store three numbers: how much red, how much green, and how much blue. And each of these usually gets 8 bits, meaning a value from 0 to 255. 3 colors times 8 bits each is 24 bits per pixel. And that's called 24-bit color. It can produce over 16 million different colors. Now, two things to decide how big an image file is. The first is resolution, simply how many pixels there are. The second is color depth, how many bits we use per pixel. The formula for the file size is the width times the height times the color depth. Let's try the example. A small image, 100 pixels wide and 100 pixels tall, at 24-bit color, that's 10,000 pixels times 3 bytes each, which is 30,000 bytes or about 29 kilobytes. This is exactly why a high-quality photo takes up so much space and why formats like JPEG were invented. JPEG cleverly throws away tiny details your eye won't notice to make the file smaller. Exam tip: that formula gives you an answer in bits, so remember to divide by 8 to get the bytes, and always write the formula down to earn the method marks. Now sound. Sound in the real world is a smooth, continuous wave. Think of it as wiggly line that never jumps. But a computer can't store something smooth and continuous. It can only store separate individual numbers. So we have to chop the wave up, and that process is called sampling. There are 3 words you need here. So let's go slowly. The first is sampling rate. This is how many times per second we measure the height of the wave. CD quality audio measures 44,100 times every second, written as 44.1 kHz. The more often we measure, the more accurate the recording. The second word is quantization. Each time we measure the wave, the value we get is rounded to the nearest number we are allowed to store. That rounding is quantization, turning a smooth value into one of the fixed set of steps. The third word is bit depth. This is how many bits we use for each measurement, and it controls how precise each one can be. So how big is an audio file? The formula is the sampling rate times the bit depth times the number of channels times the number of seconds. Let's do the 1 second of CD quality stereo sound. Stereo means 2 channels, left and right. So that's 44,100 times 16 bits times 2 channels times 1 second, which comes to about 172 kilobytes for a single second. A whole song would be tens of megabytes uncompressed, and that's exactly why MP3 compression exists. Exam tip: stereo means 2 channels, and forgetting to multiply by the channels is the most common mistakes here. Video might sound like the hardest one, but it's actually the simplest idea of all. Because video is really just images and sound that you already understand. A video is nothing more than a sequence of still images shown one after another so quickly that your eyes see smooth movement. It is exactly like a flipbook you might have drawn as a child. Each individual image is called a frame, and a typical video shows around 30 frames every second. On top of that, there's an audio track running alongside, kept perfectly in time with the pictures. Now, because each frame is full image, and we just learned that images are big, video files become absolutely enormous. Let me show you just how enormous. A single 10-second clip of standard high-definition video completely uncompressed would be nearly 2 gigabytes. 2 gigabytes for 10 seconds. that's totally impossible to stream over the internet. And this is the whole reason that compression methods called codecs exist. For example, you may see the names H.264 and H.265. Those are the names of the codecs. A codec squeezes that mountain of data down to a size you can actually download and watch. Here is a real-world point to remember. This is literally why services like YouTube and Netflix are able to exist at all. Without compression, streaming video simply wouldn't work. Exam tip. If you are asked why video needs compression, don't just say to save space. Show the numbers. Point out that raw video is gigabytes for only a few seconds. Putting a number on it, it's what earns you the marks. Alright, we have finished learning how computers store information. Now we move to the second half of this topic, how computers actually do something with that information, how they make decisions. The tool for that is the logic gate. So what's a logic gate? It's a tiny electronic component that takes in one or more binary inputs, ones and zeros, and produces a single binary output, also a 1 or a 0. The gate follows a fixed rule to decide what its output should be. These gates are built from even tinier components called transistors, which act like microscopic light switches, flipping on and off billions of times in a second. And here is something amazing to keep in mind. These simple little gates are the building blocks of absolutely everything a computer does. Your processor, your memory, all of it, it's made from millions, even billions of these gates wired together. Before we look at specific gates, log in one convention, because we will use it constantly. The number 1 means true or on, and the number 0 means false or off. So when I say a gate outputs a 1, I mean it is saying true. With that in place, let's meet the gates themselves. There are 3 basic gates, and every other gate is just built from these. So let's learn them very well. The first is the AND gate. An AND gate outputs a 1, that means true, only when both of its inputs are 1. If even one input is 0, the output is 0. A nice way to picture it. Imagine 2 switches in a row, one after the other, in a circuit. The light only comes on if the first switch and the second switch are both pressed. The second gate is OR gate. An OR gate outputs a 1 if at least one of its input is a 1. It only outputs 0 when both inputs are 0. Picture 2 switches side by side this time. Pressing either one is enough to turn on the lights. The third gate is the NOT gate, and it is the simplest one. It has just one input, and it flips it. Put in a 1, you get a 0. Put in a 0, you get a 1. Because it reverses or inverts its input, the NOT gate is also called an inverter. On the screen, you can see the truth table for each. That's just a little chart showing the output for every possible input. Memorize these 3. Here's a tip to keep and or straight. Think of real sentences. I will go outside if it is sunny and warm. You need both. I will be happy with pizza or ice cream. You only need one. That everyday logic is exactly how the gates behave. Now that you know and, or, and not, the next 4 gates are easy, because they are just combinations of those. The first is NAND, which simply means not AND. You take a normal AND gate and flip its output. So where AND gives a 1, NAND gives a 0, and the other way around. Next is NOR, meaning not OR. You take an OR gate and flip its output. Then comes the most interesting one, XOR, which stands for exclusive OR. XOR outputs a 1 only when its 2 inputs are different from each other. Same inputs give a 0. Different inputs gives a 1. And finally, XNOR, which is just XOR flipped. So it outputs a 1 when the 2 inputs are the same. XOR is genuinely important in the real world. It is how computers add binary numbers together, and it is used to check for errors when data is sent. Now let me warn you about the number 1 mistake in this entire topic. When both inputs to an XOR gate are 1, people instinctively write 1 as the answer. But XOR means different. And 1 are the same. So the answer is 0. Please burn this into your memory. XOR means different. Get that one fact right and you will avoid the most common dropped mark on the whole paper. Let's talk about the truth tables properly, because you will be dropping a lot of them. A truth table is just a chart that lists every possible combination of inputs and shows you the output for each one. Nothing more than that. The skill is making sure you don't miss any combinations. Here's the method step by step. First, count how many inputs you have and give them letters, A, B, C, and so on. Second, work out how many rows your table needs. The rule is 2 to the power of n, where n is the number of inputs. So 1 input needs 2 rows, 2 input needs 4 rows, and 3 input needs 8 rows. Third, we have to fill the input columns by counting up in binary, starting from all zeros to ones. I will explain how you fill the tables in the next slide. And fourth, if the problem combines several gates, add extra columns in the middle for each step. So you can work across from left to the right calmly instead of doing everything at once. Now, the most important exam tip on this slide. The number of rows is 2 to the power of n. It is not 2 times n. 3 inputs give 8 rows, not 6. If you get the row count wrong, every row after it's wrong too. So always start by writing 2 to the power of n and getting your rows right. Let's put that method to work on a real example, taking it nice and slow. Our expression is Q equals AN in brackets B XOR C. First, how many inputs? There are 3 inputs. We can label them as A, B, and C. 3 input means 2 to the power of 3, which is 8 rows. So we draw 8 rows and fill the inputs by counting in binary from 0 to 1. So in the first column, as you see, first of all, we have to put 4 zeros and 4 ones. And in the second row, we have to put 2 zeros, 2 ones, 2 zeros, 2 ones. And in the last row, we have to go by 0, 1, 0, 1, 0, 1. So we have to create our table like this. Otherwise, if you mix all these numbers, so the examiners will not grade your tables. Now, just like in ordinary math, we deal with the brackets first. So we add a helpful middle column for B, XOR C. First of all, we have to handle that. Remember, XOR means different. So that column is a 1 only on the rows where B and C are different from each other, and a 0 where they are the same. Once that column is filled in, we do the final step, A and the bracket. Because it's an AND and the output Q is only 1 when both A and the bracket is 1. Looking down the finished table, you will see Q comes out as 1 only 2 of the 8 rows. The rows where A is 1 and B and C happen to differ. Everywhere else, Q is 0. See how breaking it into that middle column made it manageable. Here is the exam tip. That intermediate column is not just for show. It is where you actually earn marks. And it stops you trying to juggle 2 operations in your head at the same time. Always add those middle columns and you will get the higher grades. Exam questions love to take a real life situation and ask you to turn it into a logic. So let's practice that skill with a car. Picture this: a car should sound an alarm when the engine is running and the driver has not fastened their seatbelt. Our job is to turn that sentence into a logic expression. Step 1, and this is really important, define your inputs clearly. Let's say E stands for the engine, 1 if it is on, 0 if it is off. And S stands for the seat belt, and 1 if it is fastened, 0 if it is not. Step 2, translate the English words into logic. The word AND becomes an AND gate, and not fastened means we need the seatbelt input to be flipped and inverted. So that's not S. Put it together and the alarm Q equals E and not C. Now we build the truth table to check it. When we work through all four combinations, the alarm only sounds only Q only equals 1. On the single row where the engine is on and the seatbelt is off. And that's exactly what real life should do. No annoying beeping when you are parked, but a warning the moment you dry off unbuckled. The exam tip here is a simple but powerful. Always define your variables before you write the expression. Examiners give marks just for those definitions, and once you have defined them clearly, the rest of the questions almost writes itself. This section is for higher level students. Standard level you can skip ahead. We are going to look at Karnaugh maps, often just called K-maps. Here's the problem they solve. Sometimes a logic expression is more complicated than it needs to be, which means building more gates than necessary. More cost, more power, more things to go wrong. A Karnaugh map is a visual tool that helps us simplify the expression down the smallest version. The way it works is you take your truth table outputs and arrange them on a special grid. Then you look for the ones, and you draw groups around neighboring ones. There are some rules for the groups, so listen carefully. You only ever group ones, they were zeros. Each group has to be power of 2 in size, so 1, 2, 4, or 8 cells, never 3 or 5. You make each group as large as you possibly can. And groups are allowed to overlap, and they can even wrap around from one edge of the grid to the other. One more detail. The labels along the grid go 0, 0, 0, 1, 1, 1, 1, 0. That funny order is called gray code. And it's arranged so that the neighboring cells only differ by a single bit. In the example on the screen, all 4 ones form one big group, and that whole group simplifies down to just Q equals B. Everything else cancels out. Beautifully simple. A higher level exam tip. Always make your groups as large as possible, because larger groups mean a simple answer, and smaller group leaves easy mark behind. Alongside Karnaugh maps, there's another way to simplify logic, and it's called Boolean algebra. These are just a set of rules, a bit like the rules you use in normal algebra, that let you tidy up an expression on paper. Let's look at 3 friendly ones. The first is the commutative law. It simply says the order of the inputs doesn't matter. A and B exactly the same as B and A. Just like 3 plus 4 equals 4 plus 3. The second is the idempotent law, which sounds fancy but is very easy. Combining something with itself changes nothing. A and A is just A. A or A is just A. The third is involution, and it says that 2 knots cancel out. If you flip something and then flip it again, you are back where you started. So not A is simply A. Now, why should you care about any of these? Because every term you manage to cancel out is a physical gate that an engineer doesn't have to build. In the real world, cheap designers use exactly these rules to squeeze billions of gates onto a tiny piece of silicon, saving cost and power. Exam tip. If you are handed an expression that looks long and messy, don't panic. Scan it for these patterns first. A clean, simplified answer usually scores better than sprawling one, even if both are technically correct. The last piece of the puzzle is logic diagrams. Instead of writing logic with words or letters, we can draw it as a circuit, using a special symbol for each gate. The diagram flows from the left to the right, inputs enter on the left, travel through the gates, and the final output comes out on the right. On screen, there's a handy cheat sheet showing each gate, its mathematical symbol, and the matching symbol used in programming code. Useful for when you move between theory and actual coding. Let's read a real circuit together, the half adder. A half adder does the simplest possible arithmetic. It adds 2 single bits together. When you add 2 bits, you can get a result that needs 2 outputs, the sum and the carry. which is the bit you carry over, just like carrying the 1 when you add in normal math. And here's the lovely result. The sum is produced by an XOR gate, and the carry is produced by an AND gate. That's the whole circuit. It seems tiny, but this little half adder is the seed of all computer arithmetic. Chain a bunch of them together and a computer can add any two numbers you like. Exam tip. Whenever you draw a logic diagram, label every input and every output clearly. An unlabeled wire is one of the easiest marks to lose, so don't give it away. Before we wrap up the course, let's go over the mistakes that trip students up the most, because avoiding these is just as valuable as knowing the content. First, hexadecimal is base 16, not base 8. Base 8 is a different system called octal, which you don't need for this subject. Second, a kilobyte is 1024 bytes, not 1000. Be careful about that. Third, we have said it before, but it's worth repeating. In XOR gate, if all the inputs are same, the result is 0, not 1. 4. NAND flips the result of the AND gate. It doesn't flip the inputs. 5. A truth table has 2 to the power of n rows, not 2 times n. So 3 inputs means 8 rows. And 6, for our higher level students, in 2's complement, you invert all the bits and then add 1. You do not just flip the sign bit on its own. Here's my advice. In the last minute of any question, quickly run through the checklist against your answer. Most marks lost in this topic aren't because of students didn't understand the topic. They are lost to these exact slips, made in a hurry under exam pressure. A few seconds of checking can save you several marks. Let's finish the teaching with a single screen you can use for revision. Pause here and screenshot it. First, the good habits that make this topic easy. Always draw the place value table when you are converting the numbers. Always work out the number of truth table rows first, using 2 to the power of n. Always add intermediate columns for multi-gate problems, and always label every input and output on your diagrams. Next, the formulas worth knowing by heart. The number of rows in a truth table is 2 to the power of n. The largest unassigned value you can store in n bits is 2 to the power of n minus 1. The size of an image is its width times height times the color depth, and then you divide by 8 to get the bytes. And the size of an audio file, sampling rate times the bit depth times the channel times the seconds, again divided by 8 for bytes. The single most important exam tip for this whole topic is this: show your working. Method marks are scattered everywhere, so never just write down a final answer on its own. Show the steps that got you there, even if you are confident. And that's the whole topic. Well done for getting through it. Let's quickly recap the 5 big ideas you should walk away with. 1. Computers store absolutely everything in binary, using agreed standards like UTF-8 for text, RGB for images, and PCM for audio. 2. Hexadecimal is just a short, human-friendly way of writing binary, because one hex digit equals exactly 4 bits, 1 nibble. 3. 2's complement is how computers store negative whole numbers, and that one is for our higher level students. 4. Logic gates apply simple Boolean rules to binary inputs, and you need to know all 7 of them. And 5. Truth tables map every possible input to an output, while Karnaugh maps and Boolean laws help us to simplify them. If these lessons help you, there is a free worksheet for this exact topic linked down in the video description. So go and test yourself. And for even more practice questions and full walkthroughs, head over to thepraxisib.com. If you're studying for IB Computer Science 2027, make sure you subscribe so you don't miss the next topic. Thank you so much for watching. I will see you in the next lesson.